Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2003 Physical Chemistry Lab. Today we are going to discuss on experiment 4, which is the ionic transport number. Now this is clearly one of the topics in electrochemistry, and if you have taken electrochemistry class, you have probably come across this topic before. Now another name for transport number is transference number. So in some textbooks you may see it as transference number. So it means the same thing. Now the definition is that of a transport number or transference number is that it's the fraction of the total current carried by each ion. And this is labeled as Ti. So I can either be positive if it's a cation, and negative if it's an anion. So ions in an electrolyte solution allow the passage of electrical current when there is potential difference between two electrodes immersed in the solution. And this electrical current is carried by cations, which will move towards the negative electrode or the cathode, and the anions will move towards the anode, which is the positive electrode. So there are various conditions that can influence a transport number, one being the electrical mobility, the other being the size of the ion that you study. Then there's also the charge of the ion and temperature as well, and so those are some of the conditions that can actually influence the transport number of the ion. So for a solution containing two kinds of ion, as in the example of this experiment where you're dealing with HCl and lithium chloride, the transport numbers of the cations and the anions are such that T plus minus equals to I plus minus over I. So it's the current carried by the cation, if it's I plus or anion, over the total current gives the value of this transport number. And because of that, since if it follows that I, the total current, is equals to that of the transport number for the cation and of the anion, so that sums up to a unity. So in other words, it is limited by this value. Okay, the sum of this is equals to unity. And at the same time, the speed of an ion in a solution at any concentration is proportionate to the conductance of the ion at that particular concentration. So in which you have this T plus minus can be that of the lambda plus minus, okay, the molar conductivity of whether it's the cation or the anion over the molar conductivity of the electrolyte. So in other words, if you find the value of this, either one of this, okay, and you have two of these values, you can actually find the transport number for the particular ion. So in this experiment, the contribution of a particular ion to the electrical current in the aqueous electrolyte solution will be determined from the ionic transport numbers by using the moving boundary method. So there is another method which I want you to also find out, which is not as accurate as the moving boundary method. The other method, which I want you to find out, can also measure the transport number, but not as good as or as accurate as this moving boundary method. This method consists of the presence of the leading solution and the indicator solution. So this moving boundary is basically the method based on direct observation of the migration of ions under the influence of an applied electric field. So in this experiment, the lithium chloride is used as the indicator solution because the ionic mobility is less of the Li plus is less than that of the H plus in HCl, and it's a falling boundary because it's moving down the tube under the influence of the current. So the key points in doing the moving boundary, okay, it involves two electrolytes, leading and indicator solutions, and they must have a common cation or anion. In this case, it has a common anion, which is Cl minus. So a sharp boundary must be established so that you can actually distinguish between a leading and indicator solution. So the concentration of the two solutions must be in the correct ratio. So before the experiment is carried out, this has to be decided. The cation should not move faster than the cation whose transport number is to be determined, and one of the solution must have a lower density than the other. So when you're doing this has to be taken into account. So when you look at your lab manual for this experiment, it boils down to this equation. So for example, this transport number is equivalent to the concentration of the AX solution. In this case, the AX solution is the leading solution. The volume moved when 1 Faraday of charge has passed, and then you have the electrical current and the amount of time taken. Now, I want to talk about the volume moved because in this experiment, an electrolysis cell is being used, and even you can't just consider the fact that you're going from one graduated line to another graduated line, because the volume has to be really precise. So we have to take into account of that when you actually do the experiment, and there are actually some tricks in the lab that one has to do. That you have to measure how much volume does it take to go from one graduated line to another one graduated line, and once you have decided what the volume is, then you can safely say that, because the electrolysis cell is actually not bought but being made by the glass blower, so it may be the size may be a little bit off from one cell to another. So this has to be taken into account. So this is what I said. This is what I meant. So this is where you have here the cartoon drawing of the electrolysis cell. So you have here where you have the leading solution. First, of course, you have to really rinse the cell well. And this is what I meant, that this is actually made by our glass blower. And so because it's made and using parts, broken parts of used parts of used glasses, so one cell over the other, the graduated lines may not be the same as in terms of volume. So before you do the experiment, you want to make sure that you want to do a simple test to ensure that you are sure from one line to another graduated line what is the exact volume, so that you know accurately from one line to another line, because you're going to time from going to this line to this line, how long does it take and what is the volume. So the volume change has to be really precise, and that has to be, and if you use another cell, from one line to another line may not be the same in terms of volume. So the other thing is that you have to rinse the cell well with this leading solution, which is HCl. Now, because you want to make sure that you can really see the boundary between the indicator solution and the HCl solution, we use this bromophenol blue to actually mark the difference. So in acidic solution, the bromophenol blue will turn yellow, and for lithium chloride, which has a pH of 8, I think, so that turns it into purple solution. So you can see the difference. So the color is really striking, so you can see, you know, the boundary between the two solutions. So you have this electrode, you have the cathode, and you have the anode. And so then you rinse this. Once you have rinsed this with HCl, and then you will fill this up to the tap and close the tap. Now you may find that there are some remnants of HCl, the yellow solution, in here, so you use a dropper to remove it. Once you have done that, okay, now you rinse this side with the lithium chloride, the purple solution. Rinse a few times until it's not contaminated by the HCl, so then you can fill in with the purple solution this side, and you add here a little bit of what you call lithium carbonate, so that you can suppress the production of H+. Okay, so yeah, so these are some pictures that I could get hold of the preparation of the two solutions in bromophenol blue, and filling one side of the cell, the cathode cell, with HCl, and then here filling the anode cell with lithium chloride and adding lithium carbonate to the anode cell to suppress the formation of H+. So you'll see here, okay, after placing the electrode in the two in this electrolysis cell, so then you actually place it inside the water bath, and once you have done that, you will open the cell tap. So this is closed, then you open the cell tap slowly before the DC power supply is switched on. Once the power supply is switched on, do not go and immerse your hand inside the water bath. Okay, so just leave it be, and then you will watch what's going on. Okay, so what you will see is that so this is a falling boundary, so when it is on, so you will see that, as you can see here, so what you need to do is, in this experiment, as you can see here, is actually for every graduated line you're going to time it, and based on, so what you're going to do is then plot the volume against time, and from there you can actually find the ionic transport number based on the equation that is given here. Okay, so we can play that again. So one of the trick of this experiment is to make sure that there's no air bubbles in this cell that can actually complicate this experiment such that it's not going to move. You don't see that moving boundary the moving boundary. You don't see any movement of the boundary. Okay, so then in this experiment also you are asked to actually reverse switch the wires, as you can see in the experiment, in the lab manual, where you swap the positive to negative, negative to positive, and you will see that it will actually go up in the reverse direction. Okay, so this is going up in the reverse direction once you actually reverse the connection. Right, for this particular lab, I do not have any assignment for you, as in no lab reports are required. However, I did ask you a question just now, that there is also another method to actually measure this ionic transport number. So what is the other method? So that's a rhetoric question, but at the same time that question may also be asked when we have a quiz, which is going to be in week 14, where we have the 1-hour online test. Now, because this is not going, there's no lab report to be submitted here, clearly because there is no nice data for me to actually give it to you to show that you have this a very good number for the ionic transport number. So that's the reason for not giving you, for not asking you to do a report. But however, questions based on these slides will might be asked in your quiz. So please also read all this, the slides, and go over it, go over the equation, understand the gist of the experiment, okay, and what actually governs this ionic transport number. And so that's the gist of this experiment that I want you to get out from. So no lab reports for this, just digest on what this experiment is about. And so I'll see you next week when we discuss another experiment. All right, okay, so thank you, and assalamualaikum warahmatullahi wabarakatuh.